Good afternoon, everybody. I would like to welcome you to today's session of the Hematology Deep Dive. I'm Ute Jentsch. I'm from SANBIS, and I'm currently the Acting Medical Director. And I have the honor of chairing this meeting today. I still remember the days when Google had just arrived and we were in a new era. And now I think it's a similar feeling that we find that AI is affecting every part of our lives, including our work. So we are very privileged today to have Tanya with us today to talk to us about big data and AI in transfusion medicine. But before we get there, let me just do a few more introductory slides for this afternoon's session. So obviously this is the Blood SA Foundation Forum, and the slide just shows you the institutes that support this endeavor. Next slide. Okay, the deep dive team here, we can see Professor Estelle Verburg, Terence Solomon, and Mrs. Michaelia Brooks. Next slide. Okay, just a few housekeeping notes. All sessions are recorded and they can be found on the website, bloodsa.org.za, under Resources Deep Dive. And then just in terms of interaction, please mute yourself during the course of the presentation. Please feel free to add any comments or questions to the chat box, and we will then respond to them at the end of the presentation. CPD points will be submitted to the Health Professional Council SA for each registered South African attendee. Please ensure the following. You are attending with your own registered Zoom link and not in a group. You need to attend for at least 1 hour, and your Health Professional Council number must be entered correctly when you sign up for a deep dive. Mailing list, you can join the mailing list via the website. Again, this is under Resources, and subscribe to Deep Dive. In terms of feedback, Blood SA and the speakers value your honest feedback, so please complete the anonymous feedback survey at the end of the Zoom meeting. This is just a slide on upcoming events, so that is SACIDS and SASMO conferences. Okay, this is Beyond Boundaries. This is for the 18th Annual Hematology Oncology Conference. You will also find the required information on the internet, information about registration, abstracts, and trade. Okay, and then now we are coming to our talk, Big Data and AI in Transfusion Medicine, by Dr. Tanya Glatt. And I would like to introduce you to her. Just on the next slide. So Dr. Tanya Glatt is currently one of the lead consultants and hematopathologists at the South African National Blood Service. She oversees patient services and the SANBIS Clinical Apheresis Program, and also oversees specialized laboratories, including the Cellular Therapy Lab, Quality Control, and the Immunohematology Laboratories. She's also the program director of SANBIS's JC-accredited hematopoietic stem cell transplant service, and also a supervisor on the course for the National Registrar Training Program in Transfusion Medicine. Dr. Glatt is an honorary lecturer in the Department of Molecular Medicine and Hematology at WITS, where she also received her undergraduate and postgraduate training. So please welcome Dr. Tanya. And Tanya, we look forward to your talk. I'll be handing over to you now.
Thank you very much. Good afternoon, everybody. I'm just checking that you can hear me. Number one, I'm going to turn my volume to maximum.
I can hear you.
Okay. And then let me share my slides. 1 second. Okay, so can you see my slides?
I can.
Great, thank you. So thank you for that introduction, and I'm very privileged to be here this afternoon. And to speak from a layman's experience, that is me, in big data and artificial intelligence in transfusion medicine. So we will look at a plain language guide to how blood banks are using data science to improve transfusion safety and outcomes. We will look at big data, what that means, AI and machine learning, genomics and onomics, lab on a chip, and patient safety. So let me start by saying that our patients are thinking that their future doctors are using ChatGPT and Twixify to pass medical school, so they better start eating healthy. And then moving on to what Elon Musk says, which is that AI is really better than most doctors. So that's most of us here. That's the honest truth, and it will become far better. Same for all jobs, to be honest, including mine. So in the transfusion medicine world, the International Society of Blood Transfusion has a journal. It's called Vox Sanguinis. That is the main transfusion journal internationally. And there were 2 reviews published recently on AI in transfusion medicine, and that is what we will be looking at today, and some of the use cases that they speak about. So this was just very recently published, this review on fundamentals of big data and AI in transfusion medicine. And we know that blood donor safety and blood donors in general are very important to the transfusion service. And there is a lot of AI in the donor space in transfusion medicine. So just at the end of last year, in the same journal, there was a review, AI in blood donor management and narrative review. So today, I hope to describe the principles of AI from my perspective, to look at some use cases in transfusion medicine, so blood donor management, predicting blood product usage, digital cross-match, and improving blood product quality, and then look at some future steps, some challenges, and some solutions. So what is transfusion medicine? We call it the vein-to-vein chain. So it manages the entire journey of blood from the donor to the patient. So from the vein of the donor donating blood to the vein of the patient receiving the blood product. So our donors, our blood is collected from these healthy volunteers. It's then tested and screened for diseases and compatibility. It's then processed and separated into different components, our red cells, our platelets, and plasma. It's stored, and there's all the inventory related to that until the patient needs the product, and then it is matched and given to the right patient. Every single step in this chain generates a gigantic amount of information, which we will look at. And so that's why transfusion medicine has quietly become one of medicine's biggest data producers. Donor cohorts and registries can actually scale to a national level. And what we've seen in some other countries is that transfusion medicine registries or donor cohorts have then integrated with broader biobank efforts. And the information there is just phenomenal of what AI can use with that when you have that amount of data. So blood establishments could actually develop into active contributors of precision healthcare and translational research. So why is transfusion medicine considered this big data goldmine? When we look at our donors, we have so much information and data on our donors. We have their demographics, we have their health history, we have their hemoglobin level, their ferritin level. We have all the answers that they've completed in the questionnaire every single time they come and donate. And we've got all of their donation history. And actually, we know one of the very best places in the world to get information on healthy people or normal people is actually from our blood donors. An excellent way to get reference ranges for healthy people is blood donors. When you're looking at prevalence of chronic asymptomatic diseases or even asymptomatic carrier states, one of the best places to get it is to look at our donors. And we know during COVID, when you look at the seroprevalence of COVID in populations or in countries even, most of the publications came from blood donors. So they are healthy, they come and donate, they're donating blood anyhow. You have a sample, you may need extra ethics, but blood is, you're already pricking this healthy person and you can get so much information from them. Okay, we also have lab results. So we have their blood type, their antibody screens, all of the quality control metrics and pathogen testing. Then we have a huge amount of inventory data. So we have product identifiers, so every single blood product, who it came from, when it was collected, when it was processed, where it was stored, at what temperature. We have expiry dates, where that product was allocated, interbank transfers. And you can imagine that at Sambus, we have 7 processing centers across the country. We have 84 blood banks. We service over 600 hospitals, and we have 400 emergency fridges. So you can imagine all the inventory data that's actually sitting somewhere that can be useful. And then we have patient outcomes. So we have their change in hemoglobin, we have any adverse events that they've experienced, transfusion reactions, and electronic health records. Genomics and omics are also important here. So if you can genotype your donors, you can have genotyping results of them, even metabolomics and proteomics. And these can be linked to donor biology and to blood product quality. So we know that certain genes actually affect how long your red cells are viable for, or how good they are at carrying oxygen, or how likely you are to become anemic or to faint. So all of that is useful information. And operational data. So we have so many devices around the country for collecting blood, processing blood. And so all of this information from the machines, including collection information, logistic records, and very importantly, our hemovigilance reports. So blood services are no longer just suppliers of blood and blood products, but we're actually evolving into population scale data platforms. And what they speak about a lot in AI is learning loops. So you have some information on a donor, and this information is what informs some product characteristics. So for example, their genetics will then determine how long their red cells will survive outside of their body. And then this in turn links to patient outcomes, because if the patient is receiving blood that where the red cells are able to live for longer, they may oxygenate their tissues better and have better outcomes, or maintain a higher hemoglobin level for longer. And then so they do better. So that patient information is then fed back to donors and back to processing standards. So information from each part of the chain in the vein-to-vein chain is fed forward and then fed all the way back. And that's what we call learning loops. Okay, so this slide really summarizes why transfusion medicine can play such an important role with the big data coming from transfusion medicine. So if you look at the pink line, I don't know if you can see my arrow, but if you look at the pink line going across, it really just shows the vein-to-vein chain. We have our donor, the blood product is collected, it's processed, it's then stored somewhere in inventory, and then it's transfused to the patient. Okay. The gray line shows all the data at every single time point during this vein-to-vein chain. So as we said, all of our donor demographics, our donor ID, the health questionnaires, the baseline hemoglobin and ferritin of our donors. And then during collection, so how much we collected, so the collection volume is very important. The initial lab results of the donor, what time we collected it, where we collected it, which donor center, etc. Processing information, so we have quality control metrics, phenotyping, all the component manufacturing records, and then the inventory, so expiry dates, where this product was sent to, into bank, or even into blood bank exchanges. You know that when you want a blood product in your hospital, it needs to come from your blood bank. Your blood bank may not have that product, but another blood bank may. So the inventory, all that data of the inventory and transfer is sitting somewhere. And then if we look at the patient, they divide it up into pre-transfusion, transfusion, and post-transfusion. So we have the AB and RH of the patient, we have their antibody screen, we have their cross-match, we have their transfusion history, and all their comorbidities. During the transfusion, we have what blood product we gave them, all the information from the bedside. So this is even things that were handwritten at the bedside, the indication for the transfusion, and or even their vital signs during the transfusion, and then post-transfusion. Post-transfusion, there's also hemoglobin and platelet increments, adverse events, and hemovigilance reports, and electronic health record outcomes. Okay, in the green line underneath, this shows you all the systems in which this data is sitting in the different chains of this vein-to-vein chain. So you can see here that that the data is not all sitting in the same system, and that's very important. So you can see that your donor information is sitting in donor registries. Okay, actually in Sanbus, our donor information is sitting in our VET system. So our blood establishment computer system, that's where all of our data sits. So our data of our donor and our data of all of our products. And then you can see, so they have here the laboratory information system. And in this, in this image, it actually overlaps. So this laboratory information system has information data from the product and data of the patient. We know that that's not the case in South Africa. The patient information sits with the hospital and the clinical unit, and the product information sits with us in the blood services. And then there's also information of the patient in the electronic health record. And we have hemovigilance registries and reports where some of the patient information, only specific patients and specific information would sit there. So you can see there's a lot of data. It sits in a lot of different systems, and these systems don't overlap. Okay. Underneath that, the like slightly orange line shows the different standards that govern the systems that store this data. Okay, so they speak a lot, and we will go into detail. We will talk about Fast Health Interoperability Resource, FHIR, and this is where people try to access the data that is sitting in these various systems. Okay, and then at the very, very top, this blue line shows us the AI touch points. So the different parts of the vein-to-vein chain where we can get useful information. So you could look at donor safety prediction, predicting who's going to faint, anomaly detection. You could look at waste minimization of the products, demand forecasting, which we will talk about, electronic cross-matching, and risk-aware electronic cross-matching as well. Okay, so how does AI work? Very simply explained. We have a predictive model. It uses predictive modeling, and what it does is it takes past data, and based on past data, it tries to predict the future. Okay, obviously, if it wants to be accurate, it needs to have a lot of past data, and the past data has to represent the population that it's predicting for. Okay, so for example, it will predict which patients are going to have a transfusion reaction before it happens. So you can identify your at-risk patients, and then you decide, do I actually want to transfuse that patient? Do I want to transfuse that patient during the day while I'm available at the bedside? Do I want to have some pre-meds, give the patient some pre-meds because they're at increased risk of a transfusion reaction, for example? It also uses predictive modeling to predict how much blood or what type of blood products will be needed on which day, and we will look at this specifically for platelets. So this is very accurate forecasting. So it will can predict how much blood you should collect, and that helps us because it makes sure we have blood products for you when you require them, and it makes sure that we don't discard blood products that aren't used. Okay, then in AI, a very big part of this is machine learning, and what this is where looking for hidden patterns in huge amounts of data. So, for example, if you have the genetic details of millions of donors or hundreds of thousands of donors, and maybe millions of donors from all over the world, you can then discover what donor genetics predict how long their red cells will last, and predicting which donors are more at risk of fainting or anemia. So you take the outcomes of the donor, and this is the feedback loop that then goes back to look at all the genetics of these donors and tries to see what is similar about these donors that have the same characteristics. And then how can we then predict for future for donors that then have those genetic characteristics? Will they have the same clinical outcomes or events? And then it uses rule-based learning. So it follows a very clear principle, like a checklist, if then. So for example, the electronic cross-matching, that's a very good example. If your blood types match and there are no antibodies found, then it will tell you that this is compatible. So it follows a very strict checklist. And then natural language processing is a very big part of AI. This is basically where the machine, so the computer reads, understands, and generates human language exactly like a human would. But because it's a computer, it has the ability to read massive amount of information. So, for example, it can read through adverse events reports and spot patterns that humans would miss, because humans cannot read through all of the adverse events reports in the same frame and sitting to pick up these patterns. And AI integrates all of these systems. So it integrates machine learning with natural language processing. Okay, so one of the biggest challenges with AI is getting systems to talk to each other. I hope by now that you can see that one of the biggest things with AI is that it needs data. Okay, so the problem is that Blood services across different countries store data very differently. Hospital systems don't speak the same language. Blood services and hospital computer systems store data very differently. Patient records are fragmented across many different institutions. A lot of data is handwritten, so it's in paper-based form, or even if it's not handwritten, it's literally hard copies, or it's free-text notes. Another very big issue, which we will talk about specifically in the South African context is privacy laws, which make data across borders very complex. And if you tell a European that they must send their data of their donors or their patients to America, they will not do that. Okay, so they will not be able to share data across borders. And if we don't connect all this data, then all the data just sits in silos. So you saw that where we saw the vein chain, that data is just sitting in silos and cannot be transferred across different, even within the chain, but then across different institutions and different countries. So what we really want to do is convert data into clinical value. And this is where FHIR comes in to play. So this is fast healthcare interoperability resources. And this is basically like, you could think of it like a universal translator. So it's the global standard that lets different hospital computer systems share patient data in a common format. And the way that it shares patient data is anonymous patient data. Okay, so it connects different hospital systems. It standardizes how data is described. It protects patient and donor privacy. It works across countries, and AI tools can then be built on top of it. So you have your standard computer systems or data storage systems that is then fed into FHIR, and then further AI tools can be built on that. So it really facilitates interoperability. Interoperability between systems to make it easier to provide healthcare information to us on all different devices, so computers, tablets, cell phones, and then to allow third-party application developers to provide applications which can then be integrated back into existing systems. Okay, I'm going to explain some of the parts of AI on this slide. I hope from a layman's perspective, which I hope everybody will understand as well. So the machine learning includes 3 different approaches: supervised learning, unsupervised learning, and reinforcement learning. Okay, so supervised learning is labeled data. Okay, so this is where you tell the machine, take all this data and label it either as this or this. So for example, read through all these emails and label emails as either spam or not spam. Okay, and then once you have this, you've labeled spam emails, you then must put it in a separate folder or inform whatever the next step that you tell it to do. So that information that's labeled data. Or you would tell the machine, look through all these CT scans and tell us when there is a tumor. Okay, so you would label it either as tumor or no tumor. So that's supervised learning. There's a right or a wrong answer. Okay, and there it uses classification and regression. Unsupervised learning is where there is no right or wrong answer. Okay, so the data is unlabeled. So they look here at clustering and anomaly detection. So you just say to the machine, here is massive amount of information. Look at all of this information and try see where there are patterns or where things are similar. And where they're similar, cluster those together. Okay, so that's why when you go into Netflix, it comes up with recommendations for you to watch a series that's very similar to the other type of series that you've watched. Okay, so it will say, find all these Netflix watchers that watch this type of the same genre and then advertise to them other things in that genre. Okay, so even here you would say, here are all your donors, here are all their genetics. Look at their genetics and classify similar people together, or something like that. Even anomaly detection. So banks use this with credit card fraud. So look at all of the transactions that happen, the million of transactions a day, and pick up an anomaly and then act on that anomaly. So that's what unsupervised learning is. Okay, and then reinforcement learning is really here. It's where the computer, where it uses right or wrong, or where it uses like reward and punishment. So it it learns something over and over again. So that's how AI can beat the world, the top chess player in the world. So it just plays itself 100 continuously. It doesn't stop because it's not a human, and it plays every iteration of every single move, so that it has experienced it's from reinforced learning of all the possible options and permutations. Okay. Then there's natural learning processing, which we spoke about, where really it looks at all this masses of information and reads it and then writes it as a human would, but can look at massive amounts of information. And then neural networks, they've written it actually like a brain, so like the neural pathways in a human. It tries to replicate that. So it's the neurons are actually pieces of software that work together. And they send signals. So the one neuron will process and analyze something complex, and then will then send a signal on to the next neuron in the pathway. Okay. So let's look here. This is from the second article where I spoke specifically about donor safety and AI in blood donor management. So our donors are so important to us. If we don't have donors, we don't have blood. We want to ensure, number one, that our donors are safe, and our clinical governance committee are very stringent on blood transfusion services to ensure that our donors are safe and that we are doing whatever we can to ensure the safety of our donors. In addition to that, we want to make sure that our donors come back when they donate. So we want it to be a pleasurable experience for them. We want it to be convenient. We want it to be personalized to them. We want to know when they come back, what will make them come back, what will make them not come back, what we can do to make sure that they do come back, how we can schedule them, that it will be convenient and for them. So robotic process automation is AI can automate so many administrative and very repetitive tasks. And we have so many different, so we have almost 80 fixed donor sites in the country. We have more than 90 mobile donor teams. And so if we can use AI to locate and profile suitable donors based on specific criteria that we need, then we know which donor center or which mobile donor team we want to send out to collect specific products or to get the most amount of collections, for example, at a specific time. Machine learning for big data analysis, so you can analyze all the donor data, including their demographics, their preferences, their experiences, and predicting their behavior. And then if we can predict their behavior, we can predict their repeat donations and try to schedule things and communicate with them around that. What about predicting donor deferral risks and adverse events, and predicting blood component demand strategies? And then chatbots are great because chatbots really deliver accurate and relevant information. They can handle very simple conversations, but even complex donor queries. And then chatbots are great for scheduling appointments, for sending reminders, and then maintaining follow-up communication and really personalized communication. So AI in blood donor management is great for automation, personalization, efficiency, and this is hopefully improved donor experience and improved donor safety, and then that will ensure improved blood supply. So one of the very big areas where AI has shown promise in the donor part of transfusion medicine is in donation intervals. So currently we have fixed donation schedules. You know, if you donate whole blood now, you can only come back in a certain amount of time to donate again. That's everybody. Personalized donation intervals are based on that specific donor. So it looks at that donor's iron levels, their health, their lifestyle. So this is twofold because it ensures that we have a stable blood supply and it protects donor health and improves donor retention. So we will defer less donors because they're not coming in with a low HB or a low ferritin. When they're coming, they are ready and healthy to donate. And obviously it's safer for them as well. So AI analyzes hemoglobin and ferritin levels to predict recovery time and recommend a safe donation interval for that specific donor. And then smart donation scheduling. So AI uses donor behavior and availability to schedule their appointments more efficiently and improved attendance. So if you're going to schedule me at a time where you know I come, if you know that I don't come on a Friday, then don't schedule me for a Friday. Or using that kind of information to ensure that it's convenient for the donor to come back. And then demand forecasting, so predictive models anticipate blood shortages, and then you can then identify which donor should be contacted based on the blood type demand, and then you engage with them on a very personal level, and you give them a schedule that's personalized to them when you know they're going to come. So now you are trying to even prevent shortages, anticipate and prevent blood shortages from happening from the outset. So the key benefits to this are reduced iron deficiency and donor deferrals, minimizing blood product wastage, improving donor engagement through personalized communication and AI chatbots. There are definitely challenges with this, and these challenges are the challenges that we see with AI in all aspects of transfusion medicine and medicine in general, is protecting sensitive donor data and ensuring privacy compliance, and then integrating AI systems with existing healthcare and blood banking infrastructure. When our computer systems were put in place and developed, they were never developed with the foresight of integrating into AI systems, obviously. Okay, this is another use case of how AI can be so beneficial in transfusion medicine, and this is called a lab on a chip. So this is a way of making smarter blood quality testing. So we know that the reason why we transfuse red cells is to improve tissue oxygenation. And we also know that once you donate blood and the red cells are out of the donor's body, they start to lose function. But we don't, and we know that we store red cells at 4 degrees for up to 42 days. Okay, we don't know, but we don't actually measure how functional each individual unit is. Okay, so we don't test functionality of red blood cells prior to issuing them to patients, and we don't look at specific factors of the donor and the processing that would affect the red cell functionality. So and we know that red cells start dying. We call it storage lesions. Okay, so the red cells become less flexible, more rigid. And the less flexible the red cell is, the less it can bend in the small microvasculature and deliver the oxygen to tissues. So red cell deformability is a very good way of looking at the function of red cells. We want deformable red cells that can move and bend in the microvasculature. So they've developed lab on a chip. Okay, what it is this tiny little, like the size of a postage stamp. It's a portable device. It's a small microfluidic device. And what you do is you take your unit of red cells and you put some of that blood into this tiny little chip, and you see how the blood moves in the little tubing. And that in real time can detect even subtle storage-related damage more accurately. So this lab on a chip gives you the functional age of your red cells in your product. Okay. So the current problem is that red cells can be stored up to 42 days, but how healthy they are really varies. So depending on donors and their age, their genetics, their lifestyle. And currently all we do is they compare it to if you go into the fruit shop and you choose your fruit based on when it was picked, the pick date or the donation date of the red cell and the product, as opposed to how the fruit actually looks, whether it's bruised or damaged or looks nice and fresh and ripe. So currently we use pick date or donation date, and we don't at all look at functionality. So your lab on the chip gives you this functional age of the blood unit. And then so you can see here there's three columns, and this is the three-pronged approach where AI uses different components and puts it all together. So first you use a lab on a chip where you get the functional age of every single unit of blood that's donated. Okay. Then there is the big data part of it. So there's big data cohorts. So your donors, your donor DNA, you have all the information about them. So for example, RED3 and the Danish blood donor study, they have a lot of genetic information on donors, and then they link back the unit, the blood unit quality with the donor who donated that unit. Okay. And so then they pick up that certain gene variants predict how quickly red cells will deteriorate, even looking at things like metabolomics. So we know that caffeine consumption right before blood donation can affect how long the red cells live for example. And then it builds a fingerprint of what high quality donation, what makes a high quality donation. Okay. Then the third component is AI matching those two. So it combines the data from the chip of how functional the red cells are. It combines that with the donor genetics, and then it looks at the patient, okay, and looks at the requirements for the patient in terms of improving their tissue oxygenation. And it matches the best blood unit to each individual patient. So we know, for example, our sickle cell patients, you would want to give them the most flexible red cells that can really last in their microvasculature for as long as possible and can be as efficient as possible. And maybe if you have another patient who requires blood post-surgery, for example, so maybe a routine patient could get a standard unit, and this optimizes your whole supply of blood. So we will still use our blood supply, but we really give the best. It's personalized, giving the most appropriate unit to each patient. So this reduces wastage of the units and also reduces adverse reactions. Okay. Another very big use case for AI in transfusion medicine is digital cross-match. So you all know very well about our traditional standard cross-match. Everybody who's visited the blood services has seen a manual cross-match where we take red cells of the donated unit, the plasma of the patient, we mix it together, and we look if there's a reaction or not. Okay, so that's manual. We obviously don't do manual cross-matching very often anymore as routine. Okay, it's not a routine test, but there are definitely some limitations with manual cross-matching. You need the staff to be present in the blood bank at the time. Human error is always possible with manual testing, and then it's difficult to track historical records manually or to go back and see, well, how did that reaction look? Was it a 1+? Was it really a 4+, etc.? So we do a lot of electronic cross-matching, but or automated cross-matching, and then we also do electronic cross-matching. So currently, electronic cross-matching follows specific rules, and it's really a computer cross-match. So it verifies ABO compatibility, and it checks for the patient for their antibody history. So we need to have blood grouping on at least 2 different occasions, and we need to make sure that the patient doesn't have any antibodies, and then we could use electronic cross-matching. AI has taken electronic cross-matching or digital cross-matching to the next level, okay? Because if you have the DNA, if you have the genetics of your patients, and you have the genetics of donors, and you have hundreds of thousands of donors, and you have now the antigen, you have the antigen, this allows you to have the antigen profile of all of your patients. And the antigen profile can find donors that are suitable for your specific patient. Okay, it's gone even further because, so those are red cell antigens. Okay, so that's really like giving antigen matched blood. And you can imagine in patients, your chronically transfused patients, your sickle patients who are most likely to be alloimmunized, that is amazing if you could give them really antigen matched blood down to, or including all the clinically significant red cell antigens. But it also includes HPA, so your human platelet antigens, and your HLA antigens. So electronic cross-match can be used even for platelet cross-matching, for example. And there are obviously definitely limitations with digital cross-matching, but it's an electronic, so there's no human that is doing the cross-matching, and there's a full audit trail. Obviously, in order to have this, you have to have a database of patients and them being typed, and you have to have a database of donors and them being typed for it to even be relevant and implementable. Okay, so AI for platelet forecasting demand and reducing waste is being done currently in different countries. So we know the problem with platelets is that they have a very short half-life. Okay, so 5 to 7 days at most, and they cost about 9,000 Rand a unit, and sometimes more. And on top of that, demand fluctuates unpredictably. So we've got products with a very short half-life that are very expensive, where the demand fluctuates unpredictably. So it's very difficult for us to ensure that there's enough platelets when you require them, but for us also not to be wasting or expiring and discarding platelets that we thought you needed, but then you didn't. Okay, so AI predicts how many platelets units will be needed each day, and it uses historical usage. So it looks at scheduled procedures, it looks at seasonal patterns within your hospital, within your patient population. And this is great because it reduces both shortages and wasteful expenditure. It is even used for patients with HP that need HPA or HLA match platelets, because if you have this big database, like we said, you could then cross-match suitable donors from a genotyped registry within seconds. And some countries have even used AI and machine learning models for HPA1A data, which for all of their population, which is very useful in predicting the risk of FNAT in their population. But if you look at the bottom of the slide here, you can see this is a center that uses AI to look at their forecasting for platelets. And you can see, so this is per day. And remember, this is so useful because within 5 days, that product is going to be expired. So the red is the AI prediction of how many platelets would be used per day, and the blue is the actual demand of the platelets. And you can see that platelet demand, you can see firstly how accurate it is, but you can see how platelet demand changes over the week. So Saturdays and Sundays, they use much less platelets. Fridays was the busiest, and then Wednesday. But you can see that the AI predictor tool that they used, it was actually so accurate compared to their actual demand. Okay. So in this slide, what they're trying to show is if you go to it's like the tip of the iceberg of AI and what we mean by that. So at the bottom is all of your data system. So where all of your data is stored in all your different computer systems, or in all your different places of your vein-to-vein chain. And then there's the FHIR layer, which is part of the HL7. So this is the platform that then goes and converts all of this data, anonymized data, into useful, readable data across many platforms, okay? Then the next layer is the back end. So now AI systems can come and take this data, which is all now in the same language, and can create different apps depending on what they are trying to use this information for. So that's the back end part of it. And then the front end is now then we as the end user can access this app via browser, mobile phone, etc., where all the information that originally came from this masses of information sitting at the very bottom at the data minefield of transfusion medicine. Okay. But it's not all smooth sailing. There are real challenges to overcome when it comes to using AI in healthcare and in transfusion medicine. So there's what they call the black box problem. So many AI models just tell you what to do. Okay, you must transfuse this unit or you mustn't, but it doesn't actually explain the why. And doctors need to understand the reasoning behind why a recommendation is made. Fragmentation. So we spoke about this, how data is sitting in all different places across the country and across the world. And we all store data differently. And if we store data differently, then this data cannot be comparable, or it cannot communicate. So what they've actually set up in Europe is PETRA, which stands for the Pan-European Transfusion Research Infrastructure. And this is to connect, so firstly to standardize the data, and then to connect it across the different European countries. The problem with this, for example, in our setting, is that so you teach the machine based on all this information that you have, and then the machine then makes predictions based on all this data that it has reviewed and analyzed. And then obviously when you pick up mistakes, you show it, you reteach it, and then it relearns and comes up with more predictions. But it predicts based on the information that it has. And if we just going to extrapolate data based on other European populations, we know that our population is different. And will these recommendations or be as useful to us, or will it be as accurate for our population? Privacy and governance is a very huge issue because donor and patient data is very sensitive, and we have local laws that restrict sharing across borders. And that's where federated learning comes in. So federated learning is the term of where the AI model travels to the data rather than the data traveling to the model. So you have your FHIR at the base of where your data is, so that any data coming from your systems, which is transferred anywhere else, is really not related at all, anonymized, and not related to any of your patients or donors. And then integration complexity. So embedding AI tools into existing hospital IT systems is very demanding and it's very expensive. As we said, systems were not designed for AI, and it requires significant investment in technology training and change management, including significant investment in your personnel, in your people, and upskilling us who were never trained in this. Bias in data, so especially in transfusion medicine. So we know that our donors, the one good thing is that our donors are healthy, but actually our repeat donors, they could possibly be unusually healthy, or what we call the healthy donor effect. So likely our regular donors aren't people who have genetics that predispose them to fainting and anemia. So if you're going to train your AI on this data, it may not work well for everybody. It may be very useful, though, to identify genes for very healthy people. And like we said, if underrepresented ethnic populations can also lead to models that perform worse in certain groups. And then the over-reliance risk. So studies show that doctors sometimes overtrust AI recommendations even when they're wrong, and AI can be wrong. So it should be used in conjunction with clinical experience. I included this article, which was very recently published in the SAMJ, Ethical Governance of AI in Healthcare, so critical reflections of the AI task team of SAMA on the HPCSA's guidelines on ethical use of AI in healthcare, what they refer to as Booklet 20. Okay, so they list 4 risks with AI in healthcare, including data protection, privacy, confidentiality, and anonymity. And their recommendations from the commentary from Book 20 is a strengthened regulatory approach for clinical AI should begin by defining what constitutes meaningful human oversight and establishing standards to prevent superficial approval of algorithmic outputs. They want robust local validation, and subgroup-specific bias testing should be required. So what we want it to be reflective of our population, validated in our setting. And then effective governance, so looking at HPCSA, SAPRA, NHREC as well. And then finally, Ubuntu-based equity benchmarks, so including language accessibility, rural inclusion, and suitability for the public sector context, so that AI systems advance fairness rather than deepen existing inequalities. So earlier this year, I attended a conference, the American Society of Apheresis and the World Apheresis Association Congress in Colorado. And the plenary session was all on AI. The closing symposium had 3 international speakers. And the reason why I included this slide was that to note the speakers, some of which are co-authors of those reviews, but really all of these speakers are medical doctors who then became experts in AI in their field. So what is the vision for personalized transfusion medicine? The right blood to the right patient. So every patient should receive a blood unit specifically chosen for their genetics, for their antigen and antibody profile, and their clinical condition, not just what we usually issue, which is the next unit on the shelf that is compatible. Zero waste, so precise demand forecasting means fewer units expired, unused, and this saves lives and reduces the cost of discarded units, especially platelets. Predicting a problem before it arises, so AI flags transfusion reactions before they happen to forecast shortages weeks in advance. And then seconds, not hours. So this is where digital cost matching comes in, where if you have these databases, you can, within seconds, you can find your suitable donor for your patient. Global learning networks, so blood banks across continents to share AI models, not patient data, but share models via federated learning so that we can all learn from millions of cases worldwide. And then therefore our models may be more accurate. And then bedside to biobank, so real-time data from the bedside to feed back into the AI models, so that feedback loop, creating a continuous learning loop that improves transfusion safety with every single patient. But really what's important is to upskill and train our current staff. So we cannot just outsource AI to AI experts. People within the field of transfusion medicine, and in all fields, people within the field are the people that must be upskilled in this field. So what are key takeaway messages? Hope I've not spoken for too long. So blood banking is a data science discipline. Every single step of the way from the donor to the patient generates a huge amount of rich data, and AI can make this data work better for donors, for patients, and even on a population level. AI is already in use. Electronic cross-matching, platelet demand forecasting, machine learning, antigen prediction are systems that are being used internationally today. Upskilling of staff in the field is very important. As we said, we need to develop skills internally. Privacy preserving AI is the solution to fragmentation. So we don't want fragmented data, but so we need federated learning to allow AI models to train across different institutions without raw patient data and raw donor data ever leaving the local system. But human expertise remain essential as well. So AI supports but doesn't replace clinical judgment, and interpretability and oversight are critical to maintaining trust and patient safety. That is all from me. Thank you very much. I'm happy to take any comments and questions. As a layman in AI. Thank you.
Yeah, thank you very much, Tanya. Thank you for challenging us with a very topical topic, AI, and I guess it's up to all of us to learn about it and also to, within our institutions, become sensitized to AI. Just from me, before we take some questions from the floor, obviously my first question I wrote down is the whole ethics about this, and I really wonder how our HREX and our institutions will deal with the ethical components. You did obviously allude to the role of POPI and ethics within this, and even showed us the article that was published in the SAMJ. So I think we will hear more about that, but I think as medical professionals, the ethics around AI will always remain topical. So to me, what I see as a challenge in all of our institutions, we have so many systems, and we want to use this technology like yesterday, but how do we integrate all the systems that we have efficiently and quickly to allow us to do this? I mean, you told us about at Sanders, we have the new big system where all our donor information is available, but it was designed before AI became as topical as it is now. So I guess those are big bridges we'll still have to bridge. But I think the audience will agree with me that you've really shown us how AI can be used in transfusion medicine in day-to-day questions that we have, starting with donor interdonational interval determination and a lab and a chip. So thank you for stimulating our interest there. With that, may I first thank you again, but also open the floor to any questions. There's nothing in the chat that I can see.
Tanya, you were speaking of this Petra system that Europe is going to roll out. If SANBIS or the South African or African transfusion would be aligned, would it be with Europe? Would it be with America? Where is there already something happening to start this alignment and be ready for? You very nicely said how difficult it is, because you can't just frivolously exchange data, and you also don't want to just use European or American data as if it is ours. You can't just extrapolate. So what are you guys thinking of doing?
Yes. Okay. So thanks, Prof. Yeah, very good question. So yeah, you're 100% correct that we cannot just extrapolate information from Europe. We know that will not work. The one beneficial thing, I suppose, there's two sides to that coin, is that, and we've learned it as well with our automated genotyping and microassays, is that Europe also wants South African or African data. Because they have African patients and they have, well, not really African donors, but they have African patients. And when they want to match donors and patients, they want African samples as well, and that's why people have wanted to collaborate with us, which is important because for us to protect our rights and our resources and grow our resources locally, not just give over our information to them, but it also allows us, should it be done in the correct ethical setting, it allows us to also gain, to collaborate and then gain infrastructure and systems, etc. So I don't think we would just use a system that has been implemented somewhere else. I think the local validation is what's so essential, which is interesting that it's covered in SNJ as well. So theirs is from an ethical perspective, which is 100% true, but also just from an accuracy perspective, is that we know that genetically everybody is different and that we will need to validate things within our setting. So we won't just be able to copy and paste, or but we are fortunate that people want to collaborate with us because they want to optimize their systems and their machine learning with South African data and genetics as well. So this is not new to us, that they want to optimize using our genetics, but we can hopefully use some of that information, some of that technique to upskill and resources locally. Yeah.
That's interesting. Thanks, Tanya. Will it make blood more expensive or less expensive?
I hope not more expensive. Yeah, but the truth is that what's very important, what I did say in one of the slides, is that these things are great, and the end result is less wastage, more availability of products at the right time, at the right place, better donor safety, better patient safety. But it requires investment. It requires money investment, time investment, infrastructure investment, and upskilling of staff. So it's the aim is not to make blood more expensive at all. The aim is to make blood safer and more available and more, affordable. But I do think the implementation comes at a cost. Yeah.
Thank you. It's very interesting.
Thanks, Prof. Happy to take any other questions.
Comments. Yeah. I think you've given everybody something to think or shocked them into reality that AI is here. So, yeah, but Tanya, I really think you brought this topic. It's so, in a way, so technical and so computer-based, but you brought it really to life by giving examples how this can feature in blood safety and in donor health. And this is something that SANBS will be looking at.
Thank you.
Okay. Getting a lot of good comments here, Tanya. Excellent talk from Joachim Pottriter. AI is our new frontier, indeed. Then there is a fear in the world about AI replacing people and their jobs. Do you think people should be concerned? Thank you, Rebone, for that comment. I will let Tanya answer, but she said something very important, and that is we can't shy away from AI. We all need to be upskilled, from the lab technician to the PhDs. We can't evade this. And I think the skills of people will be used differently, will be used probably more analytical, because the work that we are used to doing, the mundane job, will be done by AI. But maybe, Tanya, you would like to add something there.
Yeah, no, I think you answered that perfectly. I don't think it is, it is definitely replacing some jobs. I think it's the matter of how we use AI, and all of our jobs will change. So it's a matter of embracing it to ensure that we still have a job by using AI. Yeah.
I just want to ask Taryn, I'm not sure how long you wait until there are no more questions. I'm very happy to stay on. But if we are done, then I'm also happy to formally close the meeting.
I think it's good.
Okay. Can I proceed, Estelle, and close the
Yes,
meeting?
and it's great to see you, Uta, and thank you for chairing. And it was really a lovely session. Thank you from our
Thank
side.
you.
Yeah.
Yes,
Thank you for
I
having
agree.
us.
So thank you for allowing Tanya to give this topic on AI and transfusion medicine. Tanya, thank you very much for enthusing us about AI. And I'm sure there'll be a second talk, and I'm sure at all our conferences we will hear about AI. So let's learn AI.
Thank you.
Thank you, Tanya.
Thank you. Bye-bye.
Bye-bye.